Okay, let's get going on this somewhat strange week. For those of you who came to lab yesterday, so we had labs yesterday, no labs today, but there are labs tomorrow, which are Monday's labs, like you might imagine, because tomorrow is technically a Monday. We also have lecture tomorrow, and if for some reason you've got some conflict tomorrow with lab, and you can't make any of the other lab times, email me, we'll figure something out. Not the end of the world. Okay? All right, so here's what we're going to do today. We're going to talk about, we're going to do a Unix tip of the day, a pretty simple one today, and one that you'll do. We're going to comment on some late work, because I sent an email to everybody. I've got some comments about handing in late work, because some people called me out on something that I didn't do, which was my fault, so I will talk about that. And then, so a number of people have said, hey, look, you gave us those 2 tests for homework 2, and then we ended up providing, and the script for provide gave us all these other errors that your test didn't test for. And my answer is, so what? That's true, right? You guys need to know how to write your own tests for various pieces of code that you write. Okay, and I'm going to show you how to do some of that today. So I'll kind of model what that might look like today, writing some of your own tests. So really, when you have an assignment, not only do you have to do the actual code that we've asked you to do for the classes and so forth, but you also have to write tests to make sure that it's working properly. I mean, trust me, how much code did you look through where there was something wrong that you didn't catch the first 10 times you went through because you didn't notice it, right? Well, if you'd written a test to test that portion of your code, that hopefully would have caught it. Okay, so we're going to go through some of that today as well. And then we're going to talk about a next data structure called a tree, right? We will go through we'll go through what trees are. We'll kind of get into that. Trees are going to take a few days because they're actually kind of an important data structure and an interesting data structure, and also one that has a number of different types of formulations, and we're going to have to dig into it. So it's kind of one of the reasons we spent a lot of time on linked lists is because trees are also linked data structures. So you'll see more of the linking thing. And by the way, you can also do a lot of recursion with trees. So we'll get to all that. All right, any questions so far? Intro stuff. All right, so the Unix tip of the day. I wanted to show you two commands. One is called CP, the other is called SCP, and they're actually they work the same way. They have the same, more or less, the same capabilities, except that CP is for copying files within your file structure in, like, if you're on the homework server, you can copy files from place A to place B. We've used that a number of times. SCP stands for Secure File Copy, and that actually is what you use if you want to get files from, say, your laptop to the server. So some people have asked questions about that, and you can always download a program that's got a GUI and all that will allow you to do that. But I just wanted to show you how you could do it using SCP as well. All right, let's go into day 8 here, which is today. And let's say that I want to, there's a file here called mainwithTests.cpp. And let's say I wanted to copy that from this folder into, we'll learn 2 things today, into the previous folder, the one right above this, which would be my data structures folder. Right? If I wanted to do that, it's pretty simple. I would type CP, and then I would type the name, main with tests, and I used tab completion to do that quickly. Main with tests, and then the previous directory is ... That means the previous directory, right? So if I wanted to copy that into there, I would do that, and then it would copy it. And if I go one directory up, cd ... and I do the ls main with tests, it's there. Okay? So that's CP in kind of its easiest form. Okay, you can also, let's see, back to day 8 again. You can also do CP. You can change the name. You can say, if I wanted to copy main with tests.cpp to some other folder and rename it something, like I happen to have a downloads folder, right? And by the way, the little tilde, that didn't come out very well up there. The little tilde sign, right? That means your home directory. So if I type tilde and then slash, that means go to my home directory and then start a path from there. I happen to have a downloads folder in my home directory, so I'll copy it from there. So if I wanted to do copy main with tests, CPU downloads, and I wanted to call it new main with tests, right? I just append the new file name on there, and then it copies it over there like that. Okay? Now, let's say I wanted to copy a file from my laptop, which I'm working on right now, to the homework server. Okay? I would do something like this. I would say SCP for secure file copy, and that uses the SSH capability of your computer, right? SCP, and it's the same exact format. Main with tests, and then I need to know who I am on the server and what the server address is. Okay? And so I happen to be cgreg at, and you can do homework. Actually, is this one going to work from, this one may not work from, well, we'll see. Yeah, I think it will. Homework.cs.tufts.edu, colon, which says, after this is all an address, basically, me at this address, colon, and then I can put it somewhere. If I happen to have a temp folder, and I'll put it there. And I can then type temp like that, and it will actually, hopefully, well, as it turns out, it won't ask me for my password, because I've got a password-less login set up. But it would normally ask you for your password. You type your password, and then bing, it would copy all the files over and tell you that it copied them all over there. Okay? And that's how you do that. If you wanted to copy all the file .cpp files, scp star.cp, and then all the .h files, star.h, and then your make file. I don't have those in this folder, but that. And then you do the same thing at homework.cs.tufts.edu, colon, and then temp or whatever you wanted to do it. Okay? So that will do it. Now, the folder needs to exist on the file on the other computer. You can SSH into it and actually make the folder. But that's how you would copy files over for using the command line. Okay? Yes, Tal.
I was trying to do this on the weekend with SCP.
Uh-huh.
And if I was like, say I was trying to copy it to my desktop,
Yeah.
all it would say desktop is a directory, but it wouldn't actually copy it there.
That's a good question. I believe you would have to do it like this. Desktop. Sometimes, well, normally you wouldn't, but if you did desktop / it would generally find it. Now, it may not have been able to find the actual, may not have been, you may have been trying to copy, or you might not have had the address quite correctly. Bruce, do you have any idea what that might have been? Yeah, you'd have to see what it was. Yeah, were you using SCP or CP? SCP, yeah. I'm not sure exactly. It might have been that you didn't have the trailing / and needed it, something like that. Oh, that's right. If you leave off the, yeah, I do that too. If you leave off the colon and then type like temp, yeah, it would make a file there and put everything into that, which is not good. Right, it's a pain. It's definitely a pain. So remember the colon at the end of the .edu. Okay. Any other questions on that? Again, there's GUI programs you can download that will do it. Make sure they have SFTP capabilities, and you'll be fine. You can copy files, drag files back and forth. OK. Questions? No? All right. Let's go into a little bit of testing. Now, I'm going to bring this one down for here, because I want to show you some of this thing. So you guys all submitted homework. No, wait a minute. You know what? I forgot. I was going to talk about homework 2. I will do that. Hang on. Before we do that, let me talk about homework 2 briefly. Or I guess it's homework on comment on late work. So I had forgotten, and I didn't actually think about putting a late policy on the syllabus. We used to have those tokens, and the other classes you had tokens, and I decided I didn't want to deal with the tokens. And then there's nothing on the website that says late policy, and someone called me out on it, and like it was, I should have had something on there. But as you all got an email from me last week that said, hey, stop providing like 3 days after the due date, especially if you didn't email me. Well, only if you didn't email me. Like, if you'd emailed me and said, hey, can I have an extension? This is the reason, blah, 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 I probably would have said yes. In fact, I don't think I said no to anybody's extension, right? I might have given you less time or more time, depending on whether or not I thought you had an excuse that warranted more or less time. But that was it, right? If you emailed me and said, hey, I need a little extra time, that's the end of it. Now, for those of you who got scared by my comment, hey, if you've got provides in there, and if nothing is provided before the due date, you'll get a 0. I apologize for being so, for scaring you, because I didn't really mean it quite that way. Look, I don't care if you provide a few hours late. I put a deadline of midnight because I respect the fact that I don't want you guys to like spend all night, stay up all night working on these assignments, right? I mean, try to get it done by midnight. If you get it done by 12:02 or 3:02, I'm not going to complain. Like, we're not going to look at it. What's the big deal, right? So I'm not worried about that. And I'm not going to go and like cut off provide right at the deadline and be done with it. That said, if you're going to need like the next day, again, just email me. Like, those are the people that I'm worried about. The people that kind of took advantage of the whole thing. Okay, that was really the thing. Just ask for an extension. End of story. Any questions on the late policy? No? I think one of the things I mentioned to somebody who emailed me was it's risky to assume a late policy of you're going to get some late points, right? I mean, if it's a due date, it's a due date. But that's all right. In fact, I don't think anybody is going to fall into this problem with late, like getting a 0 this time. So don't worry about it, unless you didn't provide it all yet, in which case, well, it's probably too late. But anyway, that's that. Questions on that? OK, sorry for not bringing that up before. OK, so now let's go into this idea of how to test your code. I will reiterate one more time. You have to test your code with methods that you design, because that's the way you're going to need to do it in real life. I mean, if you're going to write a program, you're going to need to test it somehow. And one very good way to test it is to do testing code that checks all of your pieces of your code and reports on whether or not it's correct or not. The actual reporting on whether it's correct or not is a little bit trickier than it should be in some cases, partially because of Python, I mean because of C++ and part of the issue with that. But we can set something up where you will at least get an output, and you'll be able to check and see, is that output what I'm expecting? And if you don't know what to expect, well, then you actually haven't understood the problem, right? So if you can write down what you expect to happen in a certain function, then you should be able to write something to test that function. That's kind of common sense in the sense that if you understand something, you should be able to say what it's going to do. Okay? All right. I'm going to demonstrate right now. Okay? So here's what I did. One of you, who will remain nameless and may or may not even be in this classroom right now, had the following output on your provide. I have anonymized this to the best of my ability. If for some reason it's not anonymous and somebody can figure it out, then I owe you big time, and we'll chat, and I'll probably ask for forgiveness. But I think it's anonymized properly. OK, so here's what happened. This person actually did very well on a number of the tests at the beginning, right? All these tests were OK. And by the way, some of the tests, and this is the provide script. Again, we're kind of going backwards on this. You're not necessarily going to get to do the provide to see what was wrong first. But in this case, I think it's good to show you this. So we made the simple test, the advanced test. That was what we gave you. So the person passed all those. Great. OK. And then they did some tests on, let's see, whether it compiles. That's a pretty easy one. And then this tested the constructor. This is the provide script. Tested the constructor. Then it tested the getters. OK. And then it tested the setters. And look, a lot of times, you probably don't have to write extra code yourself to test the getters and setters. I'll be very frank. They're not particularly hard to implement, right? But if you don't test those and something's wrong, a later test may fail, and you'll scratch your head for a while and be like, this looks perfect, and you go through it, but it turns out it was your setter or something is screwed up, right? Well, then if you didn't test it, that's where you end up. So you have to test kind of at the lowest level first, right? Test the basic things first, and then work your way up. All right. So anyway, this person did great on these. Did great on all the regular tests. And then we come down here. It's pretty good. Uh-oh. OK. So this says testing. This DA stands for dynamic array tester on same times. OK. All right. What this actually does says what it does, and this is like Bruce's special code for actually what it's doing, but it's checking to see if you try to schedule an event that is the same time, start time anyway, as another event that's already in there. OK, what did we say for the assignment we were supposed to do if a new event comes in and it's already the same time as some other one? Yes? There you go. Put it at the end of all the events that start at that same time. Okay, can we write a test for this? I mean, Bruce obviously did, but can we write a test for this? I think we can. All right, so let's do this. All right, here's what I'm going to do. I'm going to go into my IDE up here. I've got lots of stuff now. Right now, I just took out everything else. This is not a bad place, not the perfect place, but not a bad place to write your tests, is right in main. Right? That's the first thing that's going to run. You could have your little test suite of stuff, and it just runs right there, and it tests your code, right? That's the first. That's where you can do all your testing. You could also, of course, have another. You could have a class that you call that does the testing. You could have individual functions in some other file. I mean, you can break it up in any way you want. One of the easiest ways is just put it right here in main. Okay. All right. Let me before I do this, I know this is going to get a little crazy with the size here. So let me see if I can. I thought I duplicated this already. Hang on. Nope, I can't do that. Duplicate presentation. There we go. And then I will. Where'd it go? Nope. I don't know why I can't do these. Hang on. I'm just trying to get the font size a little bit less on this. Nope, I don't know how to do it in 1 second. Don't know how to do it. We'll deal. OK, so I know what I can do. I can close this window a little more, like that. All right, so we're going to start writing some tests. Now, I've already written a lot, so you don't have to see me typing this. But if you are going to write a test, right? If you are going to write a test, it might not be a bad idea to write down what the test is in a comment, right? So you might say something like this: tests for scheduling events that are at the same time. All right? And this wraps around because of the font size I can't change. All right. The test will do what? We're going to schedule two events at the same schedule two events to a day that that start at the same time. Okay. Hold on. No idea what just happened there. There we go. All right. Okay. That start at the same time. Right, but have two different descriptions. Now, that's not actually relevant right now, but all we need to do is have it start at the same time. OK? So some comments at the beginning might be a good idea. All right? Maybe you should write what should actually happen. Right? Well, what should happen in this test? The second event should be placed after the first event. That means you understand it. Right? You understand what you're testing. Second event should be placed after the first event. OK? Well, then maybe we should write down, and you don't have to do it exactly like this. I'm just giving you an example. But what if we write down like what the test is? Schedule an event at 0900 to 1000, and we'll call it first event. Then schedule another event from 0900 to 1000. We'll call it second event, and then print out the day. Right? I think that's appropriate. That does exactly what we're trying to test. It tests that the two pieces of code, or that the two events that are at the same start time go in there, and we print out the day, and you'll print two events. And if you did it right, well, then you should write out what you expect. Right? And this one takes a little bit of thinking sometimes, because you need to know what you're going to expect. Right? But here's what I'm going to say. Output expected, start time 900, end time 1000, first event. Start time 900, end time 1000, second event. Okay? So now we know what we're expecting. We know what it's supposed to look like. And let's actually write a little bit of code to do that. Okay? So then I normally write something like this. This is all like what I would call boilerplate for each test, right? It says something like this. All right. And you're going to just copy and paste this in your next test, right? And this is all online, by the way. It's on the website. If you want to use my example here, I'm perfectly fine with that. All right? But it's a whole bunch of couts that say, hey, I'm doing a test. I'm scheduling events at the same time. Here's my expected output. Okay? And that's it. And then I'm going to say, here's the actual output. And after here's where I'm going to start writing some code that's going to test that output. Okay? All right. So there's always going to be a little bit of bookkeeping in here, a little bit of setting up, I should say. Okay? The first setting up that I'm doing is this. I'm saying create a day. Okay? And that we should be able to do. It's just creating a day, new day. And it's a pointer. And then I'm going to create two events with the same start time and different descriptions. Event 1 and event 2, just like that. Okay, so far that's my setup. And then I'm going to actually do the little test that I said I was going to do. Right? I'm going to schedule the events. A day schedule event 1, a day schedule event 2. Now I've got two events that are in there. And then I'm going to print the day out. Check. Okay. Now we're going to say, hey, the output's ended, so I can take a look at it. And then I'm going to do this little thing where I'm going to actually ask a question. I'll go through this one here. I'm actually going to ask a question in the terminal that you have to answer. Now, you don't have to do it this way. You could print out all the responses and then look through each test individually. Okay? You could figure out how a better way to actually check the input and the output. It's a little tricky with couts and things. You can do it. It's a little bit tricky. In this case, it's not a bad idea. Instead of doing print day, to do the event CSV, which actually gives you a string of the output, which is kind of cool. Maybe we'll do that in the next test we're going to do. But here's all I'm doing. I'm saying, look, here's the end of the output. And then I'm going to check for the correctness. And we could automate it. I'm going to create a string, and then I'm going to say, is the output what you expected, yes or no? I'm going to put my input into my correct variable. I'm going to check and see if it says yes, if we actually type yes. And then I'm going to say test passed, otherwise test failed. Okay? And then, finally, I'm going to say, all right, I am done with this test. Right? I'm going to say, let's see. I'm done with the test, so I'm going to say complete scheduling events. I'm done. And then I normally put some sort of divider to say, hey, you can see where the tests start and begin and end. Right? And then finally, there's a little cleanup. You should probably do some cleanup if you're going to reuse some variables. I mean, if you don't, it's not the end of the world. But you should probably do some cleanup. And then you say you're done. Okay? Any questions on that? I know I went through the code fast, but this is all online. You can see it. Questions on how I did that test? No? Let's see if it works. Let's run this. I'll run it like this. Build succeeded. Here's what the output looked like. OK, so it said, scheduling events at the same time, expected output. This is what we printed. And then the actual output is this. Guess what? We're missing that other event. Okay? So something went wrong in this person's code. All right, well, the nice thing is we are checking whether we're scheduling an event at the same time. Okay? One of the reasons I picked this code was because this person had a perfect example for class. Because in the array, if you look here, I'll try to get this so we can see it on the screen here. OK. Here's the schedule event, blah, 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 lots of code that you don't need to worry about right now, blah, 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 blah. You look through here and you go, let's see, where is it? Checks to see if this person literally put this in the code, right? Which is cool, right? Great commenting, right, for the person that did this. Checks to see if the events are at the same time, puts the second entered event after the first. Woohoo, right? That's what our test did. Let's see what this person did. Now, so the person actually did this whole thing, and then let's see. Get start time, begin, event capacity -2, blah, blah. So kind of the train came off the tracks on this one. All right, here's honestly, I got to this and I'm like, oh man, whenever you have -2s and things like lists, you're already putting yourself at some sort of a disadvantage because you want to be dealing in like increments of 1 in many, many, many cases. Okay, so anyway, so I started looking at this and I'm like, wait a minute, I don't actually think you needed to do this at all. As it turns out, remember how we had the am I before? And I actually discussed this a little bit. And I said, if two events are at the same time, if this one's the first one and this one's the second one, is this one before this one? No, because they're the same time. It is not before. So your check up here, if you make sure this works according to our original plan, like that something that's after comes, or something that is not before goes after, right? Well, this actually would do it right. So as it turns out, the person did all this great work, put all these great comments, and then, actually, was it up here? It was, nope, it was right here. Did all this great stuff. I'm actually going to delete it, right? And we're going to try to run this again because I believe that it will probably work correctly now. With that little change, right? Take a look. OK, I just took that out, and oh, look at that. Now the actual output is actually exactly what you expected. OK, so that's what. And then by the way, I had this little test in here. Right now, I can put yes. I didn't do that earlier. Test passed. Right? Woohoo. OK, so now you've got the test, and you've done the test, and you've tested that little snippet of code to say, or that little part that says if the events are the same, we do that. All right. There are two issues with this that are hard. Issue number 1 is figuring out what tests to do. All right? I mean, we talked enough. We did talk a little bit in class about, and on the sheet it said if events. And in fact, the person who wrote this code did put this little check here because they knew about it, right? Happened to do it incorrectly, but they knew about it. And they could, and you could go and you could say, hey, that's definitely a test I want to do. I want to write a little test to check this. OK? So far, so good? All right. Let me show you how easy it's going to be to do another test. Once we've got one test, OK, let me show you how easy it is to do another test. OK. So let's go down here. So we're going to fix that one. Whoops, that's not it. Sorry. Where was the report? Here we go. OK. So we fixed this one. Same time should now work properly. If we were doing our own test, we would do that. Blah, blah, blah. More testing here. Scheduling duplicates. This is actually very, very similar, isn't it? A duplicate event, does it have the same start time? Yes. Does it have the same end time? Yeah, it does in this case. But does that really matter for the way we're only checking start times? So duplicates is actually the same. As it turns out, this code will actually, the one we fixed before fixes this new one. As it turns out too. Now you could do another test for this. Some of you guys actually wrote a little function that said if it's a duplicate, don't even enter it. Well, that was incorrect. That's why a lot of you got this wrong. That's not why this person happened to get it wrong. But that's why. So you should do it. I mean, you can do a test like that as well. It's another very similar test. OK, but let's go down to another one. And let's see. Cancel single. Cancel single. Could it be the case that you put an event in the calendar and then delete it instantly, like delete it right after that? I do that all the time when I'm doing my own calendar, like in my Outlook calendar or Google Calendar, right? I click on an event and then all of a sudden I realize that I did it on the wrong week or whatever, right? Or I did it on the wrong day or the wrong time or whatever, and I just delete it, right? So it goes in and then it comes right back out. Well, that's what we want to test. That's not a bad test. Some of you guys didn't test it. The test that we gave you originally didn't test that. All right, well, let's see. If we wanted to do that, right, cancel an event, we could actually go into our code and say, I'm going to copy all the stuff I just did for this other test. Right? Literally, I'm going to copy everything here. And I'm going to put it right afterwards. And what I'm going to do is I'm going to rename the stuff that I need. I'm going to redo the stuff that I need to. And I'm going to say, OK, well, I didn't need this one. I'm going to say test for, how about this? Canceling a single event. The test will schedule an event and then cancel it. Right? Done. Well, what should happen? OK, what should happen? Well, in this case, we should have the event should not appear in a list of event, the day events, the day's events, something like that. Right? All right, so what am I going to do? I'm going to just schedule an event. Let's say we schedule this one. Right? And then instead of this, here's what I'm going to do first. I'm actually going to print the day again. Actually, as it turns out, this person had a somewhat subtle bug. What I'm going to instead do that is I'm going to print out the export CSV function, okay, instead of print day. All right, it's because this person had a relatively subtle bug. It actually didn't crash on my machine. It did crash on the server, though. Then I'm going to do what? Then I'm going to cancel the event, and then I'm going to print out the export CSV again. Right? That makes sense. I think we're canceling an event. All right. So what's the output expected? The first time, we're going to hopefully get the event, just like that. OK? And then the second time, it's not going to print anything. Actually, it's not even going to print this. It's going to print this CSV, which is going to be, it's going to be 900, 1000, and then first event like that. That's what the output should be. That makes sense? What the output's going to be for your event? OK, now let's do this. OK, test. What's my test? See, I'm just changing I'm just like copying and pasting a test. Cancel an event. Well, a single event. That's what I want to do. Oops. OK. What is the output expected? OK, we already said that. It's going to be 900, 1000 first event, like that. All right. And that's it. Like that. Whoops. Yeah, like that. And I'm just going to delete that. OK, so far so good. Now, output. OK, here's a couple things I got to change, because I did the copy and paste. I have already created my day. I don't need to recreate a day. But I do need to get a new day. You don't want to start with dirty data, right? Because that might not make your tests come out very clean. OK, same thing. I've already created event 1, but the way I've done it was I don't need to actually delete it again. But I'm just going to create event. I'm going to redo event 1, even though it's already there. You know, might as well. OK, I'm going to schedule event 1, right? And then I'm going to print out the day. So here's what I'm actually going to do. Cout. Let's see, export, is it export CSV? Let's see. Hopefully that won't complain. It did. I forget what it's called now. Export day, maybe?
It belongs to a day.
It does. It belongs to a day. But oh, right. A day. There it is. Export day. That's what I'm going to do. Boop. OK. OK. And then I'm going to delete it, right? A day, cancel event, and the same event. Just cancel the same event. OK. All right. And then the same thing again. I am going to do a day. Whoops. Cout a day, export day, like that. That should do my output, right? All right. I've already created a string, so I don't need to recreate the string. But then I can check it again, and I will check it. And then I will say scheduling. I will say complete, cancel, single event. And then clean up again. All right. Well, let's see what happens. All right. So I'm going to run it again. And the first thing it's going to do my first test, because that's still there. Right? And then we already know that's right. So I'm going to click. I'm going to type yes. This is like a terminal, right? Type yes. All right. Actually, let me see if I can do this. Oh, there we go. OK. All right. So I did this. Now, so this is now testing cancel single event, expected output, actual output, blah. Right? It does. We're supposed to get a first event, and then this one printed the first event correctly when we inputted it, and then it printed this garbage out there. OK? So I guess that means that somewhere in the cancel event there's a problem. Now because we were just canceling one event, we can go right to that piece of code. Let's go to that piece of code and see what we can get here. Let's see. So for this piece of code, oops, sorry, it's in day again. Day, dynamic array, CPP, there it is. OK. And let's see. Cancel event, cancel event, cancel event. Here it is. All right, we know where to go. We're just getting there right now. All right, so this says for I equals 0, I is less than cancel or event count. Looks pretty good. If the event is the same event as, I like that. All right, int j equals I. J is less than event capacity. OK, so that means that we're starting at the event, and then what are we trying to do? Not as good comments this time, by the way, but let's see. This might be a place where you might want to comment here. But it looks like this person is saying, take the event at j plus 1 and back it up and move it into the event at j. So it's taking, so here's the one you want to cancel, and it's taking all the other ones and going whoop and trying to move them back up to the front, right? Can anyone see what the problem with this is? This is actually a pretty subtle one as well. This line right, well, this little for loop, what's the problem with this one right here? A couple people have it, yeah. It doesn't test if there's nothing left. Actually, there's two issues with this, by the way. But what do you mean it doesn't test if there's nothing left?
It would still try and push everything over even if there's nothing there.
Well, not necessarily, because it does start at that. We hope that the variables here would work out right. All right, but there is you're getting there. You're actually getting there. Did you have another comment?
Well, if I equals 0 and there's only one element in the index is 0, and there would be nothing in event list j plus 1. So I think it looks like it creates a default event.
Yeah, that's actually a really good point. This little j plus 1 is where you're going to get hammered on this. Two reasons. First of all, what does the person count up to? Oh, event capacity, right? We only want to count up the number of events we have, right? This probably wouldn't be too bad, except that it goes all the way to the end and then tries to grab that last little piece. Remember in the output from the output here, it said, let's see, where was it? Scheduled duplicates where is it? Here it is. Cancel single. What does it say? It actually crashed. On my machine, it didn't crash. It actually printed something out. But on this machine, it actually, like on the server, it, like, program was done. It crashed, right? And part of the reason is because it actually went too far and actually copied one too many there. Now, there are some, and by the way, there is also this issue of going up to event capacity. There's a couple issues right there. All right, so let's first change that to event count, because we don't want to do too much work if we don't have to. This wouldn't be the end of the world. And let's also do this. Even though this isn't necessarily, well, this would work. OK, would this work so far? Now, somebody else had a question, by the way. Yes? Haha, you found it. There's the other issue. The person forgot to actually make the event count less than, like, go down by 1, because you removed an event, tried to make the event count go down by 1, right? So that's the other issue. So yeah, perfect. So there's like a kind of a bunch of, like, this, you could redo this test a number of times before it would actually find the actual issue. Let's see, event list, reset the event. This part, do we even need to reset the events? I don't think we actually do, right? Let's not worry. Although the person, by the way, the person did figure out that it was event count -1. But let's do this. Oops, I don't want to, there's an extra parenthesis. Well, let's leave it. It doesn't actually matter. But in here, we do have to do something like event count minus, something like that. Good? Let's see if that fixes it. OK, the build succeeded. That's good. And then let's see if I can do this again here. There we go. Let's run it. We'll run it from the beginning. And here's our first test. Same thing before. We say, yep, we already checked the first test. And the second test. All right, so the second test was we were expecting that. Oh, look, we got that. OK, end of actual output, test passed, right? And you can provide, because you're done. OK, so you see how it's not that hard to write these examples? Somebody emailed me or said on the anonymous feedback, you didn't give us a way to test examples. Well, I didn't show you how, but it's definitely, you can make your own examples. Question?
For the cancel event that you just made right now,
Yep.
where you decrement the event count?
Yeah. Where you decrement the, I might have done it at the wrong place. Is that what you're saying?
I think so.
Let's see. If there's no event capacity, yeah, you're right. I should do it in the, wait, I should do it in the, nope, sorry. Sorry, up a little bit more. Oh, down. Sorry, I'm going the wrong way. Delete events, cancel event. You're right. If it's the same event as, you're right. I should have done it. Let's see. I think that's, oops. Hang on. Nope. Yeah, that's the one. So you're right. I should have done it right there. So I might have gotten another error when I tried other counting down tests, right? OK, good call. All right, questions on the testing. All right, so do you think from now on we could write some tests, I hope? Yeah, Morgan.
Is it okay to make functions that do parts of a function at a time? So if you had to schedule back one function, like you could schedule back at the same time?
Is it OK to make functions that do part of the assignment? No, I would not want you to do that. Yeah. Oh well. We've talked about helper functions before. Helper functions are fine. Yes, you can write helper functions. But look, you don't want to write a separate function that just cancels one single event, because if you can avoid it, you don't want to write separate functions for each individual like corner case, right? You should be able to write that right in your main, the function that's the main function. Now, sometimes corner cases are so extensive that it's a better idea to say, let's put that out there. For instance, the case of the expand array. Well, a lot of you wrote little helper functions to expand the array, because that's what we did in class. And that's not a bit, that's a corner case. When the event count equals the event capacity, you're at a corner case. You've got to do a whole bunch of little stuff. You might as well write the function to do that. So yeah, that's fine too. But don't go trying to break up every little corner case. I just think you'll have to write too much code, and your code will be too verbose. Good question, though. All right. Anything else on testing? Yes?
So for homework 2, you gave us an array with all of
Yes. I gave you the main.
Can we submit homework with our own?
Yeah, you know, I am happy with that. Bruce, you don't ever use their main functions, do you? Well, sometimes you do, but not perfectly. Yeah, if you don't feel bad about submitting a new main with extra tests in there. That's perfectly fine. Yeah, I'm not worried about that at all. Okay. All right. Other questions? Yes.
So can we create a new file that just do the testing without, so we don't alter the main?
Yeah, if you want to write a new file, you can do that. What you would do is you would include that .h file for that file in your main file, and then call the functions individually. Yeah, you could do that. In fact, you can write each one of these tests that I wrote in another function if you want. That's probably a better way to do it in terms of making your code a little easier to understand. Have a function that just tests cancel one event, has a function that tests schedule same time, but then you'll be writing a lot of functions. I mean, if I want to make it kind of easy for you to go and just copy paste and boom, do a lot of this stuff, then you can do it. So, but testing your code is super important. Okay. Questions? Any other questions on that? Okay, great. All right, let's get back into the next part of our lesson. So we've done, let's remind ourselves just what data structures we've done so far. We have done lists, which we can implement either using a dynamic array or a regular array, or we can do a linked list. We have also done stacks. Remember, you push and pop from the top. It's a last in, first out situation. We have done queues, which, by the way, for those of you who haven't done the lab, tomorrow's lab is on queues, which is kind of fun. And you will possibly learn about the, although I mentioned in the way we talk about greatest common divisor, the modulus function, right? 2 modulus 3 equals 2. 10 modulus 7 equals 3. It's the remainder when you divide two integers. Okay, 2 divided by 3 gives you 0 with a remainder of 2. Right? 10 divided by 7 gives you a, sorry, did I do that wrong? 2 gives you a remainder of, sorry, it's 3. I better get this right. All right, and then 10 divided by 7, did I do it wrong before? Oh, I did it right before? Thanks, Sarah. 2 divided by 3, right. The remainder of 2, because you're trying to divide it by 3. All right. Anyway, 10 divided by 7 goes in, let's see, 7 goes in 1 with a remainder of 3. It's the remainder function. When you're doing wrapping around in queues, okay, when you're wrapping around in queues, this comes in very handy, because if your capacity is some value, when you do the modulus operator on it, you end up wrapping around to the value at the beginning of your queue. Okay, wherever you need to. So it's actually you don't need to utilize it for the lab, but you can. Okay, so we've done queues. And then finally, now we're going to start talking about this cool data structure called a tree. Okay? One of the problems with our linked list, as we've found out, and for those of you who waited for your provide script for like 3 minutes until it timed out for your linked list thing, one of the problems with it is that for large amounts of data, the linear access time is not very good. In other words, in order to get to some value, you have to go through all the different values to get there. Now, you don't have to do that for a dynamic array. However, in a list sort of situation, if you don't know what the index is, you still have to do a search through all those different values. Okay? We are going to do this. We're going to do a different type of structure, which, remember on the first day of class I said, if you have more information about something, you can actually get like a data structure. If you implant more information into it, you get more ability to do things either faster or more efficiently in general. Okay? What we can do is we can get better access time. Okay? And next week we'll start going into what those details mean about what is better access time. How does that actually manifest itself? We'll get there. With a simple change to the linked list called this thing called a tree. Okay? We're going to look at what trees can do. And before I even describe what a tree is, okay, we'll look at what they can do. Trees are the data structure. It's not necessarily how most operating systems are actually built, but you can model an operating system file system like your files, in a tree structure. Okay, and we'll talk about that. We're also going to talk about how trees can evaluate arithmetic expressions. Remember we did that with the stack? We're going to talk about similar things with trees. Okay, eventually, and we're not going to get there today, we're going to talk about how trees can provide fast searching, like really fast searching, which is cool. All right, and then there's a couple classes we're going to get into called a set and a map class, which are kind of important as well. Okay, but I think the most interesting one is probably the fast searching, which we'll get to in a little bit. Okay, so what is a tree? I got lots of words. We'll get pictures in a minute. Trees are great for pictures. Okay, or pictures work well with trees. Tree is just a collection of nodes, much like a linked list. Okay, and you can have an empty tree as well. It's got no nodes, right? If it's not empty, there's one tree called a root. Now, when people design, when the first computer scientists designed these things called trees, they, or maybe it was mathematicians, I suppose, but when computer scientists talked about it first, they said, oh, it's a tree. It looks kind of like a tree, right? And we'll see what that means. I kind of think it looks like an upside down tree, but they have this metaphor that goes through, and we'll see all the different pieces that are like parts of trees, that are real parts of real trees, right? So there's a root, okay, which is the top node in a tree. It's like the first node. It's where everything starts. It's it's analogous to the head in your linked list. Okay, we'll call that root R, and it has 0 or more non-empty subtrees. Okay, so a tree has these subtrees that kind of fall out below it. Again, a picture will be worth all these words in a minute. Okay, and the roots are all connected by an edge. Now, an edge in this case is just a line going back to R. Okay, and a tree can have a subtree, can have a subtree, can have a subtree, and each individual subtree has lines going back up to its own previous tree. Okay, all right. I see people still writing this down. But the bottom line is the root's the important part. That's like where you start everything. Okay, in your direct file directory structure, slash is where the root is for the tree, and that's like the beginning of everybody's tree. Okay, it's where everybody's file structure starts. Now you normally don't ever see this, okay, because what you've got is you've got /h/ your username, and then /, and this is where you start out when you like turn on your terminal, right? That's where you start out in your own tree. Okay. Haha, finally an example. Okay. So this is what a tree looks like. Okay? Notice the root is at the top. It's just backwards, but whatever. Trees that grow from the sky. All right? So the root is up here, okay? And here are all these little subtrees, right? There's a subtree here to B, and a subtree to C, and a subtree to D. This D has a little tree, okay? Notice C and B don't have any nodes coming off them. Okay? D has one node coming off it. A has, or E rather, has two nodes coming off it, and then this one does as well. F actually, so A has a whole bunch of like a little directly connected roots. These are the edges I was talking about. Okay? And you've got all these other pieces. Okay? That's what a tree looks like. Okay? And again, it's just links. These like lines here are links. So A links to C, A links to B. Well, it's a little more subtle. We'll get into what's more subtle about it in a few minutes. But that's the idea. Okay, let's go through some more nomenclature here. Okay, B is a child of A. Okay, well, I guess that's part of like a family tree, not part of a. I guess this is more like a family tree if you want to think of it that way. All right, B is a child of A. F is also a child of A, and F is a parent of K, L, and M. Okay, so you have this idea of children and their parents. A is the parent of all of these guys, right? B, C, D, E, F, G. Yeah, B, C, D, E, F, and G. Okay? We will probably not talk about it, but A happens to be the grandparent to all these guys, right? And the great-grandparent to these guys. I mean, you can go down that list. Kind of like what I was saying earlier with that event class. If you end up talking more than like the grandchildren level, you probably aren't thinking your problem through very well. I mean, if you're thinking more than just the children level, if you're already thinking, hey, I have to touch somebody's grandchild in some sense, right? You don't want to actually, you want to step back a second. Do I really need to do that? Because going too far down a tree without knowing where you are or doing that, you can get into kind of bad news really fast. Okay? Here's something to note. Okay? There are n nodes, A through P in this case, and n minus 1 edges. Why is that the case? Everybody has a parent, and then the root doesn't have a parent. Simple enough. Okay? Notice also that in terms of the tree itself, you can have multiple children, but you can't have more than one parent. Okay? There's no that concept doesn't exist in trees as we know it. Okay? All right. This is where it's not children anymore. If you don't have any children, okay, we call them leaves, like as in the leaves of a tree, right? This is a leaf and another leaf and another leaf. Whoops, that one's not a leaf. Did that one wrong. Okay. So everybody but that one's a leaf. Let me change that right now so I don't. Let's see. That fill. Where'd it go? White. There we go. That's a little better. Did I mess up any other ones? No, I don't think so. Okay, those are all the leaves of the tree. Okay. Nodes with the same parent, all the ones that are the same color in this happen to be the same. They're what? They're siblings. Makes sense, right? Brother, sister, sister, brother, whatever, right? Siblings. All right? And why? Because they have the same parent. Makes sense. Okay? I guess these would be like cousins or something. Don't go there. Right? The cousins, right? No, we're not going to worry about that. You could go down that path, but don't do it if you can help it. Okay? All right. We can define a path in a tree, which is a path from a parent to its children. So the path that goes from A to P, or A to O, is A, E, J, O. Right? It's not A, F, M, F, A, E. It's just whatever the direct path is, right? There is not a path in this sense from like F to O, because you can only go downwards in terms of starting a path. I mean, there are other walking a tree methods where you can do this sort of thing. I mean, if you're in a directory structure, if you're here, you can certainly go up to A and then go down to here, right? But we're not going to stress too much about going from one side to the other. Okay, just know that that's the way it goes. All right, the length is just the number of edges. So the length from A to O is 1, 2, 3. Even though there's 4 nodes, the length is 3. How far does it take to get to O? 1, 2, 3 jumps. All right, or 3 nexts, or whatever. Okay, that's the length. A lot of nomenclature for this one. Okay, because it's a totally brand new structure. Anybody seen trees before in any other class? Oh, have you all seen trees in 11? Ah, I'm going through this way too slow then. Let's just go through a couple more pieces here. So I didn't realize you'd all seen trees. I guess I should have asked. All right. Well, the depth of a node. The depth is just the length from the root, right? Which means that the length from the root of A is 0. So the depth of A is 0. Okay. The depth of A is not 1. The depth of E is 1, 2, and 3. Okay. J has a depth of 2. Okay. The depth of the root is 0. We can go the other way. We can go from the bottom up. We can say the height of a node is the longest path from the node to a leaf, right? So the height of a node is from, let's say, F, right? The height of F is 1, because how far does it take to get to a leaf? 1, right? How about the height of E? It's actually also 1, right? Because you can go this way, but to get to the first leaf, boom, you've got just 1 there. Okay, it's a little weird because the bottom is not uniform. It's the only difference there. Okay? All leaves have a height of 0, because they don't have to go any farther to get to they're already at 0. Yes, question. Over there. And then you, yeah.
So is the definition say the longest path of height? So the height of E should be
Height of E. Oh, sorry, you're right. The longest path from the node to a leaf. Yes, I'm sorry. I did the other way around. Yeah, it's not this way. It's this way. Yeah, absolutely. Thanks. Is that your comment too? Yeah, thank you. OK. All right, so we're getting there. We're getting there with these. OK. All right. The height of the tree is the length of the root. Is the height of the root. In other words, all the way to the farthest one down, which is exactly what we were just saying. Okay, so the height of this tree in this case, 1, 2, 3. 0, 1, 2, 3, right. Okay. All right. All right, we can talk about ancestors and descendants. Kind of go back to the family tree model here for a minute. Okay. E is an ancestor of P because it comes before it in the tree. Right? K is a descendant of F. It's descendant, right? O is also a descendant of E. P is a descendant of E, etc. Everybody is a descendant of the root, except the root itself. Good? All right. All right. OK. Now the bigger question is, all right, now we've talked about what these trees all really are, how are they actually implemented? I'm going to go over one implementation which is kind of, well, it's a little bit ugly. All right? But it will show you some of the issues with dealing with these trees. Okay? We could have a node linked to every child. And that's the way we will probably do it for most of the trees coming after today. Every parent, or the parent, links to all of its children like inside its data structure. The problem is, if you go back here, the problem is that, like for this one, A has 1, 2, 3, but before, in the way back at the beginning, right, A had 1, 2, 3, 4, 5, 6 children, right? How do you actually link directly in the data structure to each child if you don't know how many children there are? It's hard. Like there's no real easy way to do that. Like if you try to link each one individually. So you've got, you can vary the number of children, right? And you don't know how many children there are in advance. When you start with a tree, you get a root, and that's it. Or you get null, but then you've got a root, and that's it. You don't know how many children there are going to be. The person who writes the code for it can actually write that in there for you. Okay? Well, here's one way to do it. This is the way that I think looks a little bit ugly, but let's see if we can figure out what it means here. We can keep the children of each node in a linked list of nodes. So A has a child. Its first child is E. E keeps a list of its own siblings. F, well, a link to its next sibling. And then F links to its next sibling. E has a link to its next sibling, but it also has a link to its first child. In fact, its only child in this case. But I has a link to its next sibling, etc. So do you see how we would walk this down? To get to A, from A to P, we have to go A, first child, E, first child, first sibling, first child, first sibling. Okay? How would you actually walk that? Well, it's a little bit tricky. You can do it recursively, which I'll show you in a minute. But this is all that the structure looks like, right? We can make it a little struct, call it a tree node. We're going to have some element in there. In this case, we'll strings of A, B, C, D. And then we have the two nodes, our first child node and our next sibling node. One of the things people don't really like about this is it's like a kind of an asymmetrical view of the world, right? It's not a particularly symmetrical view. You go down and sideways, and it's odd. But do you get that this will actually keep the tree, keep everything for the tree, right? When you've got your first child, and then all its siblings, and you've got your siblings, and etc. Okay, roots will never have siblings. Although if you combine two trees, then the root that was previously root becomes a sibling, and so forth. You can do that. Okay. We don't draw the null links. All right, that would be kind of ridiculous because there's null links here and here and here and here, and there's two of them here and one here and here and here and here and here, and I mean, don't even do them. They're there, but they're null. You do not draw those edges. Okay. Yeah. Question.
So is F and E siblings, or
F and E are siblings. Anything going sideways is a sibling.
so that means that F should be the
Oh, you know what? Yeah. What's that?
So F should be a child of A in order for E and F.
It is, right, but not the way we draw it here. Right? Take a look at this. This is the same exact picture. See how F is a child of A, but we can only keep one link. We can only keep two links in A, right? One's going to be the children, the first child, and the other one's going to be the sibling. So in this case, even though it looks a little odd, A's children are E, F, and G. Right? How do you get there? Go down to first child and then sibling, sibling. Okay? All right? And then same thing with E, sibling there. Okay? So I and J are both children of E, even though it doesn't look that way on the graph. Yes?
Why don't you just say F is a child of
Why don't we say f is the what? F is, why don't we say the f is the child of e? Because it's actually not in this case. This is what it looks like without doing the fancy data structure. It looks like this. See how f is not a child of e? It's actually a child of a and a sibling of e. Okay? So it's not in this case. I'm redrawing it this way to show you what the, what this, using this data structure, how this tree actually looks now. It's kind of hard to process sometimes. Yes?
So could we arbitrarily say that F was the first child of A and then F first sibling was
Yeah. You could arbitrarily say that. It generally depends on how you insert them into the tree. We won't really talk, well, this method is a little, if you want to order things, you have to know which is really, the first child and the second child and so forth. But you're right. I mean, in terms of this picture, if all we cared about were who is the children, who are the parents, sure, A could have its first child to F. F's siblings would be E and G, and then the whole thing would be shifted a little. But that's the only difference. Okay. Other questions on that? Just again, this is a kind of an asymmetrical view of the world, but it's a way we get around dealing with multiple children for one node, more than 2 children for each node. Okay, we will get to the next one, possibly not today, but we'll get to the next one in a little bit. Okay. All right. If we had so I promised you we'd talk about file systems for a minute. Okay. If our tree was a file system, okay, and remember, E, F, and G are actually our siblings, and they're all children of A. Okay, and the same thing here. Okay, in this case, I'm marking directories with a asterisk. Okay, and I'm not marking the files. So this is your root. That's your file. That's your directory. This is another directory. Directory. So in the root, there are only three objects, and they're all directories. Okay? In this directory, there's one file, and then another directory, which has 2 files. Same thing here. They've got a directory. We've got file, and this directory has a file. Everybody see how that works? It's a little bit tricky, but it works. What we can do with this, and you do this all the time when you do, well, not quite as much. You can get a recursive list of directories. Okay? And you can get a recursive list, meaning you list all the different files out. Okay? We can also find the sizes. So I didn't put the numbers on here, but let's say directories have a file size of 1, because it's got to take some amount of space to store it. You at least have to store the name or whatever. So it's going to have some amount of space. Let's call it 1. And all these other ones will have some other amount of data in them. Okay? All right, how might we do that? Let's see. Some code. All right, I wrote a bunch of code that is on the website that you can download. I'm only going to go through pieces of it right now. But we can have a directory entry, which has the following information. It says how big your file is. There's a Boolean value which says if it's a directory or not. And then it has a name. Okay? And we're going to say that, again, directories have a size of 1. Okay? And then we're going to have a tree node. And here's what the tree node is. We already saw this earlier. It's going to have a directory entry, which is this, directory entry. Okay? And it's going to have a first child and a next sibling, exactly like what we just showed. Okay? That's what we're going to do. Now, how are we going to actually go through and print out this file system? Well, the most direct way, or I should say the prettiest way in some sense, is the recursive solution. So let's take a look at what I've done here. Okay? All right. This is just to list the directory. Okay? I will list the directory, and I'll give it a node to start at. Okay? If you give it another node, it will list the directory from that point on, which is kind of nice. Okay? And then you give it a depth, right? And the depth is just how far from the root it is. So roots have a depth of 0. Okay? All right. So what we said is we've got our base case. This is a recursive solution. So if the node is null, we just return. Then we're going to print the name. All we're doing is printing out the listing here of files and directories. Okay, we're going to print the name. Okay. Then what we're going to do is we're going to say, look, if we are a directory, we need to print all of the children. Okay, this is where it gets a little odd. the first version I wrote of this had a really nice recursive, like super easy recursive function, but it wouldn't work for anything but the root, right? Because you could actually say list all and then the siblings, right? Your first sibling, and then it would do that. It would do everything. It'd actually do it, but it doesn't list it for this. So I modified it a little bit, made it a little more advanced, and did this. All right, look, we're going to list all of the first children, okay? And what depth are the first children going to be at? They're going to be at a depth of 1 plus the current depth, because your children are 1 lower than you are in the tree, right? Then I'm going to do this. This is the kind of not quite as pretty part. I'm going to create a temporary node, which is the next sibling. All right? It's like my next sibling if I have any siblings, okay? And then, I'm sorry, it's not if I have next sibling. If my first child has siblings, that's where we keep the siblings of our children, right? Okay? What you could do, or what we do is we have the node be equal to the first child's next sibling. So now I've got a list of siblings. And we are going to list all of those siblings at that next depth. Okay? And then we're going to just increment the next sibling, or take the next sibling's next sibling and do the same thing. And this is going to be a loop here. Okay? So the question is, how is this actually going through here? It's first going to print the node, then it's going to list all the children, then it's going to go and list all the it's going to list the first child's tree, and then it's going to list all the other children's trees as well. Okay. So let's see. I think. I don't have it there. For here, so it's going to do what? It's going to come to here. It's going to go here. It's going to go. Okay. I'm going to print the root. Then I'm going to go down here, and I'm going to print this guy. And then I'm going to go print this guy, right? And there's nothing else to print here, so this one's going to go and print its siblings, right? Well, actually, this one is printing this one is going to then print this one and this one and this one, and then it's going to go over here. This one's now going to print this one and this one. It walks through the tree very nicely, as it turns out. Okay. How do you actually print a node? Well, notice that I'm passing the depth in to the. When I do the print name, I am passing the node itself and its depth to the print name. That's because we want it to look pretty. That's all. We want it to look pretty. Here's what the print name does. It goes through a loop and says, until I get to the depth, print tabs. Right? So it's going to print a tab for every depth increase it gets to. Okay, so you're going to have a nice list of like the root, and then its children, and then its children, and it's going to look nice. I'll show you in a second. All right, and then I also said print the name of it, and I also said, hey, if it's a directory, print a little asterisk to tell us it's a directory. And then that's it. So that's all the print name does. Prints name and gives a little extra information there. Okay. All right, what's it look like? Here's what it looks like. For this tree, it looks like this. You get the root printed out, which it doesn't actually print A because of the way I have it print root. I guess I should have had it print the actual A. And then it prints E, and then it prints I and J, and those are the children of E. And then it prints O and P, which are the children of J. See how it's nice tabbed properly? And then it goes back up and it prints F, and then it prints all the children of F, boop. And then it prints G and prints the child of G. Good? All right, so that's how we can actually print out the file system. We can do the same idea with finding the directory size. This is more code. It's very, very similar to the idea. I don't want you to stress with this. If you want to go look at the code online, you can do that. But it's basically the same idea. It says get my size, right? And then get the size of all my children and all of my siblings, or all of my child's siblings, which are also all of my children. Does that recursively, and then it returns the total size at the end. Okay, that's all. And then I also had to put in a thing if it's just a file. Problem with this, if we don't ask if it's a directory, well, remember files sometimes have siblings, so if you don't account for that, you end up running into the problem where you count the sibling sizes too, and you don't want to do that. So it's a little bit ugly. Lots of code. You can go look at it in your own time. Okay. All right. Last thing I'm going to just very briefly touch on. Those trees, and I wanted to show you this structure to say, look, this is ugly, right? It's asymmetrical. It's not particularly intuitive. I mean, like we said over here, we said, look, doesn't it seem like F isn't connected to A directly. I mean, it is. It's a child directly of A, but we don't actually link there, and it's ugly. Right? It's kind of not so fun. Let's limit ourselves, okay, to this idea of what we call a binary tree. Okay? We have a special tree, and the special tree says you are only allowed to have maximum of 2 children. Binary, 2, right? Only allowed to have a maximum of 2 children. You can have 0 children, or you can have just 1 child. Okay? A has 2 children, B has 1 child, D, E, and F have no children, etc. Okay? You can have that. A binary node, you can keep the links directly there. Why? Because there's only 2 of them. You know there's always only going to be at most 2 of them. So now our binary node structure is very simple. We've got our element and then a left and a right. Woohoo! Right? We've got A's left is B, A's right is C, etc. D has no left and no right. They would be null. B only has a left and it's D, etc. Right? Much, much simpler. Yes, question?
Can't we have a dynamic array that keeps track of all of the nodes for the children?
Could you have a dynamic array? Sure, you could. It's a little trickier. We will get into that a little bit later, where we have a tree based on an array. You just have to know where in the array to go to get there. The nice thing about a linked structure is it's so simple to understand, in the sense that I've got 2 links, my left and my right, and that's it. Right? So it's easier to understand. You can build it into an array structure, sure. You just need to do there's a little bit of math involved. That's really the only thing about knowing where to jump as far as where my children nodes are, but you definitely can. And we will talk about those, especially when we get to things like heaps and that sort of thing, which is later down the road. OK. Other questions? All right, let's see what else I got here. And then, oh yeah, a couple things about binary tree. The nice thing about a binary tree, one nice thing about a binary tree is, on average, right, you only have roughly the square root of the number of nodes depth, right, which is actually kind of cool. How many nodes do you need to, on average, touch before you get to the bottom? Square root of the total number of nodes. That may speed things up a lot. In fact, it does speed things up a lot. It's not perfect. For a binary tree, you can have these weird situations where that's a binary tree, right? This one has 1 node, this one does, this one does, and this one does. This kind of devolves into a linked list in this case. If your binary tree looks like this, it's just like a linked list, right? Because you have no left nodes. You only have right nodes, and it kind of looks ugly. OK, tell you what, we'll stop there, and we will see you guys tomorrow.